In this video, you will be observing the behavior of the Quansor Cube setup for position control tracking. We have a PID controller over here, which we will be using to adjust the proportional, integral, and derivative gains. And as feedback, we have the angle in radians, which is read from the encoder. And here we have the input voltage, which is written via analog to the motor. Over here we have the Quansor Cube setup, which is right now at around 45 degrees. We see here from the steady state error that the proportional controller cannot drive the error to zero alone. As responses to disturbance, we see that it responds fairly well, but we still have a steady state error, no matter what we do. And this is visible over here. Now the target tracking is 45 degrees. Increasing the proportional gain on its own to 20, we see a very oscillatory behavior. Adding an integral gain of 10, we must see the error going to zero and less oscillations. And this is fairly visible on the graph. Steady state error is zero. Now adding the derivative gain of 0.5, for example, this would result in much larger disturbance rejection, which is visible over here. Increasing the gain even further will result in a much more difficult disturbance, much more difficult to move the motor. With the derivative gain, moving the motor is much more difficult. You can sense the resistance, and it's also visible on the graph. Increasing the gain, the derivative gain to 1, for example, will make it converge even faster. This seems to be the most perfect position control system.